Number 17. Suppose you attach the object with mass m to a vertical spring originally at rest and let it bounce up and down. You release the object from rest at the spring's original rest length. Letter A. Show the spring exerts an upward force of 2 mg on the object at its lowest point. All right. So here's a little picture. Here's like the initial case, we'll call it, the figure on the left. Basically, we're just attaching the block at this point. In other words, you can basically just think about this as the spring. This is the spring's natural resting length, and I'm just going to put this block on it, okay? And then what's going to happen is right after I attach the block here, I'm then going to let go. And what's going to happen? Well, obviously then, in the final state, this mass will go downward, right? Because gravity's pulling it down, and it will stretch the spring. So the question is, what we have to do now is at the bottom state here, we have to identify that the force that this spring is exerting here on this mass is upward, and the value will simply be 2 multiplied by its mass times gravity. All right, that's what we have to figure out. So the key insight to this problem is going to try to be, well, how can I relate the initial state to the final state? In other words, what about the initial state and the final state should be equivalent to one another? Well, whenever we feel like we don't have a lot of information, a very useful technique to use is to think about energy, all right, energy concepts. So what I could say is I could say, well, once I attach the block here, there's basically all potential energy, right, of that initial state. Why? Well, because this block is going to be at some height relative to its final point, right? This block is at some height whether I take it from the bottom to the bottom, or whether I measure that from the top to the top. That's okay. You don't want to measure from the top to the bottom because then you're being inconsistent, right? But it doesn't really matter. We know that this block has some potential energy to it due to gravity because we know once we let go, it's going to drop down. So I know there's potential energy in the problem due to gravity. But then I'm going to ask myself, well, all this potential energy then gets converted to what? Well, eventually, it's all going to get converted into spring potential energy. But along the way, it's going to also be converted into kinetic energy, right? Think about it. This block, as soon as you let it go, it's going to begin to move. Once it begins to move, you know there's kinetic energy. So what's happening is the potential energy due to gravity is decreasing, all right? And the kinetic energy is increasing, and the spring potential energy is also increasing, right? The further this mass drops, the further the spring is going to be stretched. Therefore, the potential energy within that spring, right, is also increasing. Well, once the spring gets to a fully stretched position all the way down here, right, it's all going to be then potential energy in the spring. So that's the key. The initial state's all potential energy due to gravity, and the final state will be all potential energy due to the spring. So if that's the case, we must know then conservation of energy states that the potential energy due to gravity in the initial state, or all the initial energies, will equal then all of the final energies, which in this case is just the potential energy inherent in the spring. Now what I can do is I can expand on these two things. All right, so notice how simple this is, right? I mean, look at the formula is not hard, but getting to the concept is a little bit. All right, so now here it's going to be potential energy due to gravity is mass times gravity times then the height, right? And more specifically, it's really should be change in height, okay? Because it's always relative. And that shall equal now the potential energy due to the spring. And that's a formula we have over here, right? That's going to be equal to 1/2 force constant, okay, or spring constant, multiplied by, again, I keep doing this change in the position of the spring from rest length squared, okay? Now the key here is to, well, one of the keys, well, that was the first key. Now we need a second key. There's another door, right? And then another door, and another door. Right? It's like that never-ending box of whatever. Anyway, I don't really know what I'm talking about. So the next step in the problem is going to be to realize that this change in height, or the difference in height between the initial point and the final point, is literally the same thing as the change in x, right? I could have called this y. Maybe that would have been a little better. I'm just keeping it x. It doesn't really make a difference. As long as you understand the fact that the change in height from the initial point to the final point is exactly equivalent to the change in length of the spring from its equilibrium point. That being the case now, what I'm going to do is I'm then going to plug in now my delta x in here. I'm going to leave out the negatives for right now, okay? I'm not going to plug in any negative yet. Now what I realize is that I can indeed cancel this x squared on the left, right, with one of the x squareds on the right. So now I'm left with this. mg equals 1/2 k x, k delta x, right? And now what I'm going to do is I'm going to move this 1/2 on over to the left, meaning I'm going to divide 1/2 out on the right. In other words, I would multiply by 2, right? I mean, that's the same operation. So we're going to realize now we're going to have 2mg. Ooh, we're getting close now, right? That's kind of, I'm realizing I got to get to 2mg, and I'm realizing, well, here's mg and here's a half. So how the heck does that become the same thing? Well, easily, right? Just divide out the half. So this is then equal to k delta x. Now what I'm going to do is I'm basically going to I have to understand that this delta x is a negative value, right? So now I'm going to plug it in, okay? So what that means is now this, I'm just going to plug in that negative sign there, okay? And then the last step now is to step back and see what you have. Realize that this negative k delta x is the same as this negative k delta x in the formula over there for Hooke's law. Right, so Hooke's law is f is equal to negative kx. So what can I do? Simply now plug in f. And notice here now f is positive, right? And the answer here, right, it's all positive. There's no negative value. So this, we just proved it, okay? Yeah, all right, let's take care of that. So letter B. If the spring has a force constant of 10 newtons per meter and a 0.25 kilogram mass object is set in motion as described, find the amplitude of the oscillations. All right. So first thing to note is that if you were to think about what happens here, okay, first pretend that, remember, this picture, we are initially holding the object, then all of a sudden we're going to let go, and the mass is going to fall down to this relative height. What happens, though, after, like, let's say, a few minutes, that it's obviously going to stop, right, eventually. And the block is going to reach some equilibrium length. Where do you think that equilibrium length will lie? Will it lie in between the two? Will it lie lower or higher? What do you think? Well, it will lie in the middle, right? Think about that. You know that when you release this block, the gravity is pulling down pretty hard and there's kind of acceleration to it. So the block is going to go past its natural equilibrium length. And it's going to oscillate now. Once it reaches the bottom part, it's going to oscillate back up. And then it's going to come right back down and then back up and blah, blah, blah. Eventually, though, over time, it comes to rest. So the resting length is probably going to be somewhere here, right? Right in the middle of the two. Okay? Now, what's important here, I know the picture's getting a little jumbled, but what's important here is to note that the amplitude is the difference in height of the equilibrium position and, let's call it the initial rest position, or the final maximum stretch of the spring. It doesn't matter how you kind of define it there because they're both going to be equal. Basically, whatever the difference in height here from the top of the initial unstrained length to the equilibrium length will be the same as the distance from the fully strained length to then the equilibrium length. Okay, so they're going to be equivalent. So it doesn't matter to me how you think about it. All you have to know is that it's basically going to be the amplitude is 1/2 of this maximum x. Okay, so I'm going to write that down. Amplitude, because I just mentioned, right, it's either going to be this distance or basically this distance, right? So I wasn't really consistent in the picture there, but it would be middle to middle, okay? And then of the box, and then I could measure it from middle to middle. I could measure it from top to top, and then bottom to bottom if I wanted. I could measure it from top to top here, and then top to top there. It doesn't matter, right? They're all the same. So the amplitude is going to be, again, equal to 1/2 of the maximum change in the spring's length. Okay, just keep that in mind. Now that we fully discussed amplitude, now we can kind of figure this out. So for part B now, it says find the maximum amplitude. So first of all, they told us the force constant and they told us the mass, right? Well, what does that allow us to find? Well, if you look at the formula, right, we have over here, that allows me to find the change in height, right? The change in x, the max, essentially, the max. This is really max change in length, okay? So what that means is I'm going to do that. 2mg is equal to negative k delta x max. All right, and now just plug in. So 2, the mass was 0.25, gravity is 9.8, the spring constant was 10, and we're going to solve for delta x. So when we do that, let's take out the calculator. So it's going to be basically 2 times 0.25 times then 9.8, all divided by negative 10. So we get a negative 0.49. Now remember, this is the max, okay? But we want to know the amplitude, not the max. So notice that amplitude is just half of that x max, right? So A will then be equal to 1/2 of this thing, negative 0.49. Now the amplitude, technically, you can just take the absolute value of it, all right? Because the amplitude, it's either going to be a positive value going up here in the picture, it's going to be a negative value. So just take the absolute value. It doesn't really matter, all right? So just take half of this number, and we realize we're going to get a number of approximately 0.245, all right? And that would be, in meters if you want. Not if you want, but I mean, that is in meters. All right, so there you go. So that's the amplitude, all right? And probably I should have, probably 2 sig figs here if I look at it. So 2.25, whatever. It's all close enough. Who cares about sig figs, right? Your professor might, but I'm not grading you, so don't worry about it here. Find the maximum velocity, letter C. So for this question now, we have to take a look at the formula over here where it says that the Vmax will be equal to the square root of the spring constant divided by the mass multiplied by capital X. Now, I do not like that notation myself. A capital X there in the equation is amplitude. So I'm going to change that. I'm going to say Vmax, right? The maximum velocity that this thing can obtain will be equal to the square root of the force constant k, or the spring constant k, divided by the mass of the object that's oscillating, all multiplied now, not under the radical, but all multiplied now by the amplitude. So that's the formula. Just plug it in, right? So we have then square root of k, which they told us was 10, the mass was 0.25, and the amplitude now we found was 0.245. And voila. Let's do it. So square root of 10 divided by 0.25, and then take that answer, multiply it by 0.245, and we get a value of about 1.55-ish, right, considering rounding, and meters per second. And that's the max velocity that this thing can obtain. And that's it, ladies and gentlemen. All right, so thanks, guys, for tuning in. Hopefully this helps. Please remember to help us out and subscribe, and we look forward to helping you with more problems. Take care.